So today I'm going to cover some concepts of DNA sequencing, and then I'll show you some of the tools that we have on our clusters. We'll be using the GRACE cluster, and we'll be running some job scripts, or at least one job script, and then going over some other useful tools on the cluster. So how many of you have accounts, HPRC account? Has everyone been using GRACE? Have you been using GRACE? Everyone has? Okay. We'll cover some things, maybe some new things here. Just a reminder, your password, your login and password is for your account only. That's linked to your A&M, your official A&M account. So you don't want to share your HPRC account login with anyone else. And we're going to take a break about halfway through here. This is the what we're going to cover today. The first part is just going to be mostly discussion, talking about DNA sequencing, and then we'll finish it with towards the end, we'll talk about containers, and if we have time, we'll download a container from Docker Hub and see how that works. Okay, we have a few ways you can access the cluster and run tools on the cluster. So how many of you have used the command line before? Familiar with the command line, the Unix commands? Okay, you can use the command line. That's once you get used to using the command line, you'll see how useful it is, and you do have to learn Unix commands and find an editor that works for you. But it's a great way to work on projects, and especially when you have a lot of files and a lot of different jobs. Working your way on the command line is very useful. You can use the portal. The portal has access to the command line, but it also has access to other tools that have a graphical user interface, such as RStudio, or you might use JBrowse or maybe Jupyter Notebook. So those are available on the portal. You can look at the list. When you go to the portal, you click on interactive apps, and these are apps that are designed specifically for a job to launch on the compute node. So when you do launch these jobs, you are charged service units while the job is running. So when you're doing an interactive job, let's just say you schedule a job for 7 days. You're not sure how long it's going to take to process, but it's better to overschedule or overestimate the time than to underestimate the time and your job to end on a Saturday morning or something like that. So if you schedule it for 7 days and you work on it, say you start today and you work on it and you finish this afternoon, then you want to cancel the job and you'll be reimbursed for the service units of the remaining 6 days. But using the command line on the portal, you don't get charged service units. And using the command line, logging in using the command line, you don't get charged service units. You just get charged service units when you submit jobs. Also, if you're using Galaxy, when you submit jobs in Galaxy, you get charged service units. But to actually use Galaxy and upload files, download files, you don't get charged service units for that. So whichever way you're most comfortable, and whichever way maybe in your lab's a lot of people in your lab work on the command line, it might be useful to learn to use the command line. All right, if you do have Windows, you'll need to connect to, if you want to use a terminal, there's an application called MobaXterm. Does anyone have Windows computers? Okay, have you used MobaXterm? How do you connect to the cluster? Do you use the portal, or do you use PuTTY or something else? Is anyone connected to the cluster from Windows? Nobody? Look, the portal. Okay, so if you want to use an app that's installed on your computer, on your Windows computer, you can install MobaXterm. We have a lot of users that use MOBA Xterm, and we can provide support for using MOBA Xterm. It's really kind of like the portal, because the portal, you have a command line, but you also have a file browser, file system browser. So you can view the file system and you can view images from the portal, similarly to how you use MOBA Xterm. So connect to the portal, you go to portal-grace, whichever cluster you're using, portal-terra or portal-faster, and then our hprc.tmu.edu. And then you can click on the clusters tab and select the shell access. And this will get you to the shell. So I'm going to do that. You can also go from the main page here, our main page, and click portal, click portal, but you mouse over portal and then Grace portal. It'll take you to the portal. And then you can connect to, here's where you can browse files, either in your home directory. We'll go over that later when we create some files. Grace shell access. And then I'll log in. I'm using a YubiKey. That's why you saw that string of characters. You might use the Duo app or a phone call to do the two-factor authentication. So when you log in, you can see your quotas. By default, your basic account has, or your HPRC account. When you get an HPRC account, you have a home directory of 10 gigabytes and 10,000 files, and that doesn't change. If you're filling up your home directory, then you'll need to move files to your Scratch or else delete some files. Sometimes there's a hidden directory like .conda or .local that gets filled up when you're installing some software. Then you can move that hidden directory to your Scratch directory and then create a symlink in your home directory. So all those files are counted against your Scratch quota, not your home quota. So the home directories are backed up nightly, but they are overwritten each day. So if you accidentally delete a file in your home directory, you can request us to replace it that same day. But if you wait a few days, then it will not be available. Scratch is not backed up at all. You get 1 terabyte and 250,000 files. You see my quotas are larger than that because I do a lot of software installation. Let me see. There we go. Okay. So you can request a quota increase for your Scratch if you're working on a big project. So you need about 5 terabytes. You can send a request. Work on your project. It is a temporary increase for 6 months. And when you're done with your project, we ask that you download your files. You can create a tar zip package and download that. And then you can delete your files from the cluster you're on. But just verify that your download is complete. Once you download your project, just unzip it on your local system and make sure all your files are there before you delete the files on the cluster. All right. All right, so I'll use the term node often, or you might hear it in a response from our help desk. So when we talk about node, there's actually 2 types of nodes. We have the login node. So right now, I logged into Grace 1. We have more than 1 login node. If you log in, you might land on Grace 2 or Grace 3. So the login nodes are a place where you can do file manipulation, upload, download data, use the text editor to create job scripts, or you can do some simple tasks that take less than 60 minutes. The processes on the login nodes are automatically stopped when they reach a 60-minute mark. But you can do some testing of software and upload data. Even downloads will stop at 60 minutes. So we have a data transfer node, and we also have another application called Globus. So if you have a large group of files you think is going to take longer than an hour to download or to transfer to the cluster, then you'll want to use Globus, and we have that on our website. Or you can just ask us to make sure, and we can direct you to the Globus documentation. So when you are using the login nodes, you can test your software, but you'll need to limit the software to 8 cores. On a login node, there can be different clusters have different number of cores on the login node. So like on Grace, if one cluster has 28 cores and we have 10 people all using 8 cores, it can get overloaded. So sometimes someone will run a piece of software, and that software doesn't have an option to limit the number of cores, and it just grabs all the cores and starts running. So when you are running on the login node testing software or doing something, just make sure that your processes aren't using more than 8 cores, because we do have scripts that will monitor this, and if it does, we'll let you know. Sometimes you're just unaware. Users are unaware that the software is just grabbing all the cores and running, and sometimes there's no way to control that with the software. So just keep an eye on the processes. Your processes, you can use the top command to do that, and it'll show you how many processes you're using. So the compute nodes is where all the heavy computational work is done. So anything that's going to take longer than 60 minutes, or anything where you're going to want to use the entire compute node, all the cores, all the memory, or you want to, if you have software that supports running on multiple nodes, then you'll want to submit a job script to the job scheduler, which is called Slurm. And then job scheduler will find available compute node resources and fit your job on any available resources. Okay, I'm going to talk about some sequencing technologies, and then we'll look at some sample data. So this is just a list of some of the software, the DNA sequencing technologies. Notice the HiSeq's not up here. It is been, the manufacturing has been retired for the newer sequencers, but there are still sequencers out there, the HiSeq sequencers. You can see what's new. The iSeq is very small, like a printer, and that's interesting because if you have any problems with it, you just mail them your iSeq, and they mail you a new one. If you have any issues, it's so small they can just handle it like a small. They don't have to send out a serviceman to come look at your system. You just mail it in; they'll send you a replacement. So single in, paired in, we'll talk about these in later in one of our, I think we have, yeah, we'll cover this in one of our job scripts. So single in sequencing basically is just you have a double-stranded DNA and you're only going to sequence one strand. This is dependent on the type of analysis you're going to do. You can ask your sequencing center which is best. Obviously, paired in data, you're going to get more sequence data, but you may not need to pay the extra cost to get paired in sequencing because single in sequencing may be enough data for whatever you're doing. Mate pairs are created a little differently. You can see single and paired in. The DNA prep is a fragmentation step, and you get a fragment size. A fragment meaning a double-stranded DNA fragment of around 200 to 500 bases, sometimes smaller. And then you have these adapters on each end, and you can sequence the forward and reverse strand if you're doing both or just the forward strand. Well, mate pair is different. You have the first Fragmentation step are very long fragments, 10,000 bases, for example. Then there's a circularization step. There's a junction. It's highlighted here where you see this this green part here. And then there's another second fragmentation step, and then all of these fragments that don't have the junction are washed away, and you're left with this mate pair here. This mate pair, if you map it back to the genome, is going to be whatever you're selected your fragment size, your insert size for, which in this example is 2,000 bases. So the fragment size here is 400 bases, but your insert size is 2,000 bases. Insert meaning if you align it back to the genome, that it'll span 2,000 base pairs. So paired in is just an example of what you might see. 400 base pair fragment. If you do 100 base pairs read length, MiSeq does up to 300. So, but the large sequencers don't go to 300, but let's just say you just have 100 base pair read. Then you'll have a section in the middle that doesn't get sequenced, but you have enough coverage where you're able to, when you're doing assemblies or alignments, you'll be able to determine that region because you have multiple DNA fragments. And then you have a FASTQ format files. Here's the pair. They're maintained in order. The first the first entry of each of these files is the same DNA fragment. And in the past, there's been some software where when trimming is done, the order is not maintained. But a lot of the better software will maintain the order when reads are trimmed. If you do have a problem with after trimming, if you have like 10,000 reads in one file and only 5,000 in the other, then they're not paired. They should have the same number of lines. If you have that problem, there are tools where you can pair the reads up again, so you'll have the same number and the corresponding IDs for each entry. So for example, this first part of the string here, that's identifying the flow cell and the flow cell ID and the coordinates on the flow cell. And then you have like, this is a number one, that's read number one, and then read number two. And this is all the same because it's the same sequencer and the same coordinates. All right. This is what I mentioned earlier. You want to maintain the read pair order. Sometimes all the fragments are the exact same length, especially if they're the shorter fragments off of one of the larger sequencers. The MiSeq can do some initial trimming. So you might see the forward reads are one length and the reverse reads are a different length. And notice like L3, this little fragment in the middle, there could be some overlap where you have sequencing from both ends, and there is actually some overlap. So there's a region that you sequence twice. And that can be useful in some cases, and I'll show you how we can take advantage of that region. All right, this is a different type of sequencing technology, Oxford Nanopore. They have this, this is from an image from their site. You can see they have this tunnel looking pore thing here, and DNA is unzipped and one of the strands goes through here, and there's some electrical current that passes and measures the chemistry of what passes through. And you can get really long reads off of this. You can get a 5,000 without 5,000 bases in a row as compared, which is different than the 5,000 base pair mate pair. So you got actually a long read of 5,000 or more bases. It does have a higher error rate, but there are ways to correct and improve the error rate. This sequencer is very small. It's actually kind of like, it's smaller than a cell phone. The one on the left here, you can see it's hard to tell, but that's really about the size of a cell phone. And then you have almost like a cluster of these you can link together. And these are These are very useful if you're working in the field. You can take a DNA sample and sequence it right away. PacBio is different technology, and the sequencer is very big. That sequencer is about the size of a refrigerator. But you can see the read length distribution. You can get reads up to 60, 70,000 bases long. So that's pretty good if you're doing assembly, or you have a targeted region you want to explore more. These can be useful. The error rate is a little higher than the ChIP-seq or the Illumina reads, but there are ways to use a combination of PacBio and Illumina reads for certain analysis. Here's how the PacBio works. They take a double-stranded DNA and they put these templates on the end. They call it a smart bell template, and it's basically just a loop. It loops the top strand with the bottom strand. Then they have this polymerase that attaches to the double-stranded DNA and starts sequencing. Actually, probably attached to the template, and then start sequencing, and to go around the template and go along the forward or reverse strand, and then go around to the other strand, and just keep going until the reagents wear out and the polymerase falls off. So then this longer strand here in the middle with the different colors, you can see that it sequenced the template, then it sequenced the top strand, it sequenced the template again as it went around the loop, bottom strand, top strand, bottom strand. So you can get all of these what are called subreads and create a consensus sequence. So this consensus sequence is more accurate than if you were to just take one of these reads, because the error rate is a little higher for this type of sequencing. If you have a 70,000 base fragment, you're not going to get as many subreads as you will from a 5,000 base fragment. So when you have a 5,000 base fragment, those reads are going to be more accurate because you're going to have more subreads to create this consensus sequence. And so this is kind of like I mentioned earlier, these hi-fi reads they're going to be shorter. This x-axis shows from 0. Let's just say this is 50,000 bases long. The long reads can get up, the average here is about 40,000, but the accuracy is about 50%. With the hi-fi reads, they are shorter. The average fragment length is shorter, or the fragment length is the same as the insert size. That's actually shorter, but because it's shorter, and the way the sequencing technology is, the shorter it is, the more subreads you have. So you have a higher accuracy for these hi-fi reads. I don't know why they put this in the middle. Usually the y-axis is over here, but this is just saying even the short reads have high accuracy. These are probably comparing the Illumina short reads, that the hi-fi reads can be just as accurate as the short reads, but they have a lot longer length. All right, we have a number of tools available if you have a PacBio sequencing data set. Minimap 2 is very popular. Canoe is very popular if you're doing assemblies. And then Unicycler is good for bacterial genomes. Another one that is really, it's really fast compared to Canoe. It's accurate, but not as accurate as Canoe. But you can get a good draft assembly quickly, very quickly, like 10 times faster than Canoe if you use this WTDBG2. Fly is another one that's a popular one that's being used. When you're done with your assemblies, there are some ways to improve the assembly, and we have that in the Aero package, which is AeroGrid. We have a module called AeroGrid HPRC that's on Terra, and Purge haplotigs on Terra. Haplotigs are, for example, if you have a diploid genome, when you do an assembly, if you have a region chromosome 1, for example, on one of the homologous chromosomes, and that same region on the other homologous chromosome has an insert size or a significant difference, you're going to get 2 assemblies for that region of chromosome 1. So what Purge haplotics does is it takes the largest contigs, and these are called the primary contigs. So for example, you've sequenced the entire, let's just say chromosome 1, you've got eight regions assembled for chromosome 1. 5 of those are actually the primary contig, and 3 are the homologous chromosome. So these are called the haplotigs, the ones that aren't. The haplotigs are the ones that are not the primary assemblies. You can divide a diploid assembly into its primary contigs and the haplotigs, and that's what purge haplotigs will do. It will divide that for you and create a mapping of where this haplotig will map on the primary contigs. Because if you do a diploid assembly, you're going to get you'll probably get regions on chromosome 1, the same region that's a little different into 2 different contigs, and then it appears that your genome is actually larger than it is, but you've actually just have a second part of a region of a chromosome. All right, tool suite. SmartLink is provided by PacBio. This is a list of some. I'm sure there's more now since I've made this slide, and maybe some of these are different, but you can see some of the useful ones in here. There's Minimap 2, there's PB-Align, BLAST-R, that's a useful one. BAM-to-FASTA, BAM-to-FASTQ, those are useful. There's a lot in there. I don't know what they do, but you might find something useful in there. PBMM2, I think that's PacBio Minimap 2. That's their own version of Minimap. All right, so I mentioned you can have a combination of long reads and short reads. So if you have PacBio sequencing data and you follow up that project with Illumina reads, then there are assemblers that you can use to use both of these types of sequencing technologies. Spades, Mazurka, and Unicycler, you can generally you will build an assembly using the Illumina reads, and then you'll use the PacBio to verify the assembly and maybe to join contigs. All right, let's talk about some tools, how to use these, where to find them. You can go to our website. We have I'll just click on this. I'm just going to go to, from our website, you can go to up in the top right, there's this W. That's actually the Wikipedia icon, but it's not Wikipedia. It's MK Docs. So from here, actually, there's another menu here. You might see the menu already, but I have to click these bars. You can go to software and then click on bioinformatics. And then you can click this category overview. So this gives you an overview of not all the tools, but some of the tools that we have documented. There might be some special thing you have to do to get this tool to run on our clusters. And so we have some information on that. So for example, let's just look at RNA-seq, and then on the right, I'm going to look at Trinity. Okay, so it shows you how to look for the module. These are commands you run on the command line: module, spider, Trinity. It's not case sensitive, so you don't have to use capital T. But there's some information here about the temp directory, how to use the temp directory, when to use it. And then there's an example job script of how to use that temp directory in your job scripts. So this might help you to get started. Check our webpage. This is built. This bioinformatics tool category is built off of a lot of what our users, feedback from our users, and also from us working through these tools. So this is this was started basically when I got here about 8 years ago. So there's a lot of information here that can help you get started. Some of it might be old. Maybe there's software that has a newer version now, but on the web page, it might show an older version. If you want to use a newer version, most likely the commands are the same. If you want to use Trinity and you notice we only have version 1.0, for example, and there's a 1.5 now, you can request a newer version to be installed. And we don't just update every software every time it's released. So it's because sometimes someone will request software and then they'll finish their project and graduate, and then no one else uses that software. So if you see a newer version on the website, the software website, just ask us and we can install it, the newer version. All right, so module spider tool name. So let's go to our and just do, I think I lost my session here. I think I'm gonna have to log in again. Okay. Module spider Trinity. So you can see we've got several versions here. And then if you look at the bottom left corner, it says lines 1 through 26. If I hit spacebar, I can see more and it finished. Sometimes you've got a lot of output, and then you can scroll back up and see what versions. When you want to load this version, just copy and paste it and instead of trying to type in all the dots and dashes. You can search for keywords, and this will actually show you all the descriptions that have the word assembly in it. And there's a lot here. You just hit space bar. And if I was to do that again, and I didn't want to go through all of that, I can just hit Q to quit. All right, there's a useful website here. If you have long reads, PacBio or Oxford Nanopore, there's a lot of good tools listed here. Some of these we don't have installed, but if you see a useful tool on that website, this is really good. They keep it updated. And if you see a tool that you want to use and we don't have it, let us know. We might be able to install it. There are some tools that are on Anaconda, don't show up in Module Spider. So if you don't see a tool, ask us, and we might already have an Anaconda environment for it. So we're going to just go through this, how to load software. So if you want to work through this, loading software on Grace and Faster, our newer clusters, is different than loading it on Terra. We used to have a way to directly just load a module, but then it was very confusing because we have these tool chains, and people would mix tool chains and libraries would get out of order and the software wouldn't work correctly. So now we have this module hierarchy, and basically you load the tool chain first, the basic tool chain, and then you load the software. And once you load the tool chain, then you can see all the software versions that are available with that tool chain. So let's just say we're going to, if you're on the command line, is anyone connected to the command line and want to work through this? Okay. So you may already know this, but I'm just going to go through it. Some may not be familiar with this. You can type in bowtie or bowtie 2. In this example, we're going to search for bowtie 2. Okay, we've got several versions here. I'm going to hit Q to quit, and we want to load 242. 242 right here. I'm going to highlight it so I don't have to type this in. Okay, so module spider, I can't load it yet. I'm going to show you what happens if you do module load. It's going to say you can't load it yet. It says run module spider before doing module load. And it will show you how to load it. So once I do module spider, now it says, you got to read this line carefully because sometimes you have more than one line and some users will try to load everything on all the lines, but you only need to load all the modules on any one of the following lines. In this case, there's only one line you need to load. So I'm going to copy that. I queue to quit, and I'm going to do module load. I'm going to paste that there, and then I'm going to go ahead and copy the bow tie. Copying and pasting in your computer might be different. This is a Chromebook, and you can see there's a little copy and paste icon that pops up. And I just hit Control V to paste. Sometimes you can double click. If you're using a terminal, you can double click it and it will copy it. And then you can use the scroll wheel, the middle mouse scroll wheel, and click that and it will paste it. For a Mac, I'm not sure. So then module load, this is what I have, 10.20 is the tool chain. The tool chain is just the compiler version that was used to compile the software. All right. So I didn't get any response, which is good. If there's an error, it'll say something's wrong. If there's no response, that's good. So now we can do module list. Now you can see number 15 is the actual module that I loaded, and number 4 here. So, but we've got all these other modules. These are libraries that were used when the software was compiled. So you'll see a lot of these. Sometimes you'll have like supporting software that's needed or that can be used with Bowtie. For example, Bowtie is loaded, but also Python is loaded because Bowtie needs Python. So you don't have to load Python and then load TBB and then load Bowtie 2. You just load Bowtie, and there's a lot of dependencies that get loaded with it. All right, so now I want to look for SAM tools. I want to see what version of SAM tools is available. If I do module spider SAM tools, it's going to show me there's a lot of versions. I hit Q to quit. But if I want to see which of these versions are compatible with my current environment, I do module avail SAM tools. And it shows me, out of this list, it shows me that 111 is compatible with my current environment. So then I can load SAM tools. Okay, module load SAM tools. Then you can do module list. So SAM tools, you can see SAM tools also picked up this. So between Bowtie and SAM tools also has an additional dependency called CURL. But SAM tools also is using these dependencies, GCC core 10.20. All right. Does anyone have any questions about this step? It takes a while to get used to Spider and Avail, the difference between Spider and Avail. Avail is what's available to load in your environment. Module purge removes everything that's in your environment. So you can say have no modules listed. So when you run your job script, you're going to have module purge, which should be your first line. And then, so you start out with a fresh environment, and then you load your modules, okay? At the end of your job script, you don't have to do module purge because the environment is going to go away when your job is complete. So you should only put module purge at the beginning to start with a clean environment, load your modules, and we'll go over that. But you can see the difference here between module spider, which shows you everything that's on the system, and module avail, which only shows you what's available for your current environment. If I was to do module spider, module avail, okay, there's nothing available because I don't have the dependencies loaded. So you start out with module spider, and then you can see the list, Q to quit. Then to know any one of these I want to load, you do module spider to get more specific details. All right, does anyone want some additional time to work on this, or we're ready to keep going? Anybody have any questions? Okay, keep going. That's pretty straightforward. So tool chains, sometimes some software uses GCC core and Another software might use GCC. So what's the difference? So if you type in the command tool chains, I'm going to hit Control L to clear tool chains. It's going to show you which of these FOSS tool chains corresponds to the GCC compiler version. Okay, so if you load FOSS 2019B, it also loads GCC 830. It's not shown here in the blue part, but it also loads GCC Core 830, and it also loads this OpenMPI module. Okay, it doesn't load Python, but if you were to load that and do module eval Python, it would show you which Python version is available. Now, if you just load GCC 830, it also loads GCC Core 830. It doesn't go back and load the FOSS, and it doesn't load OpenMPI. If you just load GCC Core, it only loads GCC Core. It doesn't load GCC, and it doesn't load FOSS, okay? So sometimes you load GCC Core in one module and do module eval, and the other software module you're looking for is not available. But if you load GCC in addition to GCC Core, the same number, then you might see some more software that's available, okay? And if you just want to, if you're going to load multiple softwares, it might be easier just if you see it says to load this software, use GCC Core 830. You can use this table and say, instead of just loading 830, instead of just loading GCC Core 830, I want to see what everything's available all the way up to FOSS. I want to make sure I'm finding all the software that's available for this toolchain. Then you can just load this FOSS and then do module eval, SAMtools, Bowtie, whatever, if you're loading multiple modules at the same time. In your job script, if you're doing a workflow, you can like module purge, load some modules, run a certain step, do module purge again, load some different modules, run a different step, and go on that way. Sometimes if you have all the software in the same tool chain, then you can load them all at the top. But if not, you can do module purge and module load different versions, because we have a software installation framework called Easy Build, and some of the newer software uses the newer tool chains, but some of the older versions of the software have the older tool chains. So if the newest version of a software was released 2 years ago, it might have an older tool chain that's not compatible with software you're using that was released last week, which will probably have the newest tool chain. So then you can do the module purge, module load approach. All right, there is a temp directory on the compute nodes. Remember, the compute nodes is where the computational work is being done. This is automatically created at runtime. You can't see it on a login node. There's no value in there. But whenever you create a job script and launch that job temp directory will get created for that job script. Now, the temp directory is a flash drive that's on the compute node. So when you're writing to the temp directory, it's like going from the motherboard directly to the attached flash drive. Okay, it's going to be, in some cases, it'll be a lot quicker than trying to write back to scratch, especially if you have thousands of files. So when you write back to scratch, you're writing across the network that everyone else is using to write. Okay, so if you can use the temp directory, use that. It might speed up your work. And also, the files on the temp directory don't count against your quota. So you can write 500,000 files on the temp directory. If you don't need those files when the processing is done, this is the best approach. Just write it to the temp directory, create those 500,000 and delete it. If you try to write 500,000 files to scratch, it could take longer, but also you may reach your quota and your job fails in the middle. Then you got to request a quota increase. It might take a day or two to get approved. And then you got to go back and start over. Okay. So take advantage of that temp directory. And usually it's about almost almost 1.5 terabytes. So it's pretty big. And, but just remember, if you schedule a job using only half the node, then anyone else that's using the other half, they also have access to that temp directory. So if you want to have all 1.4 terabytes available for your job, request the entire compute node, all the cores, all the memory, and that your job will be the only one on that compute node. So you'll have the temp directory all to yourself. This is just an example of how to use it. In this case, this is a Picard tools. It has an option to specify a temp directory. Some software does not, but if it does, it can be useful because really the temp directory is a place like doing some processing. It writes files that you really don't need when the processing is done. All right, so we're going to talk about QC evaluation. And once you search for FastQC is very useful to do some evaluation. It will take about 200,000 reads from your files. It will create some images of quality scores. If there's any contamination, you could probably identify contaminants such as adapters, or if you actually have maybe you sequence 2 organisms. The organism you were sequencing and the person in the lab got their DNA mixed in there. You can find ways to see if you have mostly one or multiple organisms that were sequenced. That's based on GC count. You can either run the GUI or run it on the command line if you have 10 files or so and don't want to wait for it. You can just run in the command line and then come back later and check the output files. FastQC uses just 1 core per file. So if you have 1 file, you don't need to reserve the entire compute node to process 1 file. Most of the time, it's pretty quick. If you're going to do 1 file, you can do it on the login node. But if you have 20 files or more, just do it on the compute node and use 1 core per file. All right, digital normalization BBMap is, I think it's a really useful tool. They have a lot of different subtools in there are available. You can do digital normalization. There's error correction. There's overlap correction. Remember I showed you how the pairs are overlapping when you sequence? BBMap, there's a tool within there that can find these sections and do error correction. Basically what it does, if the overlapping regions, if one of the bases don't agree in both reads, it takes the quality score of the base, the highest quality score of the base, and it will correct the others. Or if it can't determine, it will put an N in there. You can merge those reads with BBMap, or you can error correct without merging. Normalization is good. Some people say, I don't want to throw out data. I don't want to use all the data I get. It's wrong to throw out data. Well, it's not wrong. For example, some software will say, we recommend 50x coverage to do this analysis. And if you sequence on a high-seq a bacterial genome and you get 3000x coverage, you need to find some way to normalize that data down to 50x. It's not going to do you, if the developers of the software recognize that 1000x or 3000x coverage would be better, they would say 50x is good, but if you have 3000, that's better. But usually they don't. So you want to scale that down. And the way to do that is you don't want to just take the first 10% of the sequence files. You want to you want to take a subset of that, and you want to do it across the genome. So you have a uniform coverage of 50x, for example. So BBMap will handle that for you. Trinity does an automatic normalization now to 50x. So if you have 300x or 500x in your RNA-seq data, by default, Trinity normalized to 50x because they recognize that you don't need 500x to do this type of assembly. All right, template job scripts. So we'll go over this and then we'll, this section, then we'll take a break. So we have a lot of template scripts. These were developed as we installed software. We tested them. We have some example test data. And basically we create a job script that you can use as a template. You can run this directly. The job script, it has the example files already. So if you want to get used to or get familiar with running job scripts or just see how other people have created job scripts and what can be useful inside of a job script. And these are good templates. So to access this, you just run the command GCA templates. Okay, I hit GCA and hit tab, GCAT tab, and that fills in. So I think I need to come, let's see. Okay. So these are the categories. These don't match up with our documentation. Remember I showed you different categories. It's not a direct relationship. So these are a little bit different, but there are some here, or there are some on the documentation that aren't here. But not all tools that we have installed are here, but we do have a lot available on Grace, not so many on Faster or ACES. But as we get new clusters, we'll need to update that and add more. So let's just say we wanted to, what are we doing here? Let's go to, okay, I was going to show you this. I think we still have the web page open. Okay, so Trinity. We do have a documentation for GCA templates here, but under this, you can see we have a template for Grace. And if you click that, it will show you what the template looks like. You can copy and paste this if you're browsing on a documentation, or you can search for this directly on the command line. It might be quicker on the command line. All right, so let's go through this. We want to make a directory first in our Scratch. Scratch is a variable that has a link to your Scratch directory. So I'm going to hit quit here, clear the screen. So if you're unfamiliar with Scratch, the variable, it's all caps with a $, and it just holds the name of your Scratch directory. So we want to make a directory called NGS_class. I'm going to have to update this slide because it looks like you can't see that underscore right there. There's an underscore right there. Don't put spaces in directory names. Sometimes people name their file on their Windows computer with spaces and they upload it to the Linux and it has spaces in it. It's going to haunt you later. So don't use spaces, use underscores or even dashes. I need to correct this slide, but let's just do this. Scratch NGS_class. All right. There's no error. If I already had the directory, it'd say, hey, this exists. Do something else. CD scratch. So CD. I can actually hit tab here and it will make sure I'm not typing in something wrong. Tab is very useful on the Unix command line. You should really make it part of your work process. Get used to that tab. It will save you. It can save you a lot of time. So from here, our working directory is the directory I created. Now we're in here. LS, there's nothing in there. So now I'm going to run GCA templates. Okay, so in this example, we're going to select number 2, and then we want to find a template for FastQC. And then when we get to the end, it will save that template script to our working directory. Okay, you can do number 2 is FastQ files, QC. We know that. And then FastQ quality evaluation, screen contaminants, quality trim. FastQC is quality evaluation. So you can select number 1. Okay. There it is, FastQC. There's only one tool available. If we had multiple evaluation tools, you'll see multiple tools. Or maybe you'll see FastQC 0.11.8, FastQC 0.11.9, different versions. So there's only one option here. And then this is a basic tool, so we only have the defaults there. So sometimes you might have a template that's designed to work for paired-in files, and sometimes you might have a template that's designed to work for PacBio, for example. So now it says, do you want to copy the script to your current directory? Shows you the script name. You can type Y and it'll copy it. But what I'm going to do is I'm going to go back home and I'm going to search for FastQC. Okay, S to search. Now it took me there. Let's just say you want to find Trinity quickly and you don't want to go through that first few menus. Just search for it. There it is. And you can continue from here. Number 1, defaults. Do you want to copy the script? Yes, I want to copy it. All right. There's a reminder that it's just a template script. You'll want to, when you use it for your software, you want to adjust the SBatch parameters. If you have a larger data set, most likely you will, because we're using small data sets just so the job will complete quickly. But with FastQC, again, that you only need really 1 core per file. You can look on the web to see if there's a newer version. If you want to use a newer version and we don't have it installed, let us know. Or you can just search the command line here for a newer version. So maybe there's a newer version of the software, but we don't have a template for it. Most of the time, you can just replace the newer version into the template and it'll work. But sometimes software will change their options, and so the template for an older version of the software may not work for the newer version. But you can try it out. Most of the time, it'll work. All right. So now we can see we have that template script. Let me make this bigger now. Okay, there's the template script. So notice the color is green. So green is an executable script, which means you can run it directly. Other colors are like white. Generally, that's just a text file. An image is purple. If you have a PNG image, the color will be purple. And directories are blue. So if I make a directory, make an output directory. This can be totally dependent on your terminal and how you have the color set. Sometimes it is kind of a little hard to read, but you can see output is blue. That's indicating it's a directory. So it helps you know what these are without actually doing ls-l. ls-l gives you some more information. You can see this output over at the very first digit here is a D that says it's a directory. That means it's a directory. Notice that it's not a directory, but it has the X in 3 places here. So X means executable. If it has X here and it's not a D, then it shows up as green executable. Okay. So this is an example of what the template script looks like. We saw it on the web. SBatch parameters at top. These are recommended parameters. Notice this CPUs per task up here is 2. You can use this variable called slurm, CPUs per task, all underscores in uppercase like that, with a $sign there. So if you're going to scale your job and next time you want to use 48 cores instead of 2, maybe you're doing some testing with 1 file, then you want to use the entire node, you can use this value down here. So later you only need to change it here. So this value is going to be taken from here. And in this case, I'm saving it into a variable called threads. And then I can use that variable in my command right here with a $sign threads. So to assign a variable, you don't use a $sign, you just say threads equals. But to use the value that's in the variable, you use the $sign in front of the variable name. Okay, and we also have some useful information here, a README file. you'll want to do this. You want to document your job script, what you did, because 3 months later, your PI is going to say, okay, what did you do? What version did you use? Why did you do this? And you're going to go back and say, oh, I forgot. Let me look at my job script. And you didn't put any comments in here. It's going to help you to put comments in there. Why did I, this is kind of a simple job script, but why did I do this one step? Put a little comment in there. So I'm doing this because I did some research and found that this is the best way. You might even put a link to the web page. It's good to comment your job scripts, because a lot of that information, or some of it may be asked later by your PI or when you're trying to publish, right? And then we also, at the bottom, we have a link to the software. You want to cite the software. A lot of this open source software is funded based on how often it's used. They'll evaluate how often it's used based on how many times it's cited. So if you're going to use software, you'll want to cite the software in your publication. Even if you use seven different tools, you want to cite all of those, include one for each of those. And also, we ask that you acknowledge us, and we will add you to our acknowledgement page. So if I can research citations. So we have we keep a table here. As users let us know they use us they cited us in a publication, and you can see over time, really this is when we started getting our large clusters. We had a lot here, but then COVID came along and we had fewer publications, and this is just a case where we might just have need users to let us know so we can add it to there. All right, as long as I'm here on the main web page, you can see how busy the clusters are. So if your job's not starting, check here, see if the cluster is really busy. All right, so let's go ahead. We'll go a few more slides and then we'll take a break. So there's a tool called Max Config. Let's just say you're working on Grace and you don't know what is the total number of cores available on the compute nodes and how much memory can I use in my job script. It's different on each cluster. So if you're working on whichever cluster you're working on, you can run this command called max config. It will show you the maximum cores, memory, and time for the default partition. You can select a partition, and maybe the GPU partition, the max time is only 2 days compared to the CPU partition, which is 7 days. This is useful because it'll give you all that information. It'll give you all this information in one step here. It'll search other commands like sinfo. It'll also let you know if there's a maintenance coming up. If you were to submit a job script with these parameters, it'll let you know there's a maintenance coming up, and if you submit this job now, it's not going to run. But right now, this is a 7-day job, and because this, for using CPUs only, the maximum runtime is 7 days. You can use 48 cores on the compute nodes. There's 48 total in this partition. Right now, the partition is this long partition. You can see the number of partitions here. If you want to use the big mem partition, then you would specify that partition. Notice this has 48 cores and 360 gigabytes. If you want to change the partition in big mem, see what's available on the big mem nodes. You can see there's 80 cores and there's almost 3 terabytes of memory. The more cores you have, the slower they are. They're a little bit slower, but most of the time you'll want to use these lower. 360 gigabytes is going to usually be enough for your jobs. We do have, if you're running an assembly, most likely you're going to need most of the assembly jobs, people that have been using the large memory nodes. Notice the job runtime is shorter. So for basic jobs, you don't want to just grab a large memory node because it has 80 cores. You're not going to be able to run it more than 2 days. If you are doing an assembly and it reaches it's about to reach the 2-day mark, your assembly is not done, let us know. We can extend that. But if you're doing fast QC for more than 2 days on the big memory node, we're going to notice that, and you don't need the big memory node to run that. We're not going to extend your job. We're going to say take it to a smaller node. The regular nodes have 360 gigabytes, which is more than enough for fast QC. So be aware before you just run and select the big memory node. Make sure you really need that much memory, because we do have users that do need that memory, and there's not a lot of big memory nodes, but there are a lot of the 360 gigabyte nodes. All right, so you can so gedit is a graphical user interface text editor. You can launch that from a terminal, or if you're using MobaXterm, I don't know. I think you can launch it from MobaXterm, but from the portal you can't launch it from the portal here. You can't launch gedit because this is a web-based portal and it doesn't have a way to launch the GUI from the web. So you have to use a different editor if you're using the terminal. I'm sorry, if you're using the portal. So let's come back to the dashboard. In that case, you can use the file browser. Here, this file browser. Okay, it'll show you. It's still loading. It should see I'm in my Scratch directory, Scratch user, and my username. And these are different directories. You can see these are directories like a folder, and then I've got files here. You can create files like here, new file. If you want to edit a file, there's an editor. You can create your files here. If you're using the portal, it's good to use this. You can create files. Go to a specific directory, create the file in that directory, and then you can come back to the command line and see that file and run it. If it's an image file, you'll need to come back to your Scratch space, and then you will need to, you can view image files from here, but you can't view image files from here. So let's go ahead. This is just a command. If you are using a terminal, you can use that editor. If not, you can use the portal editor. Or if you're familiar with VI, VI is really useful. It's a command line editor. It does take some learning to use. There's a lot of commands, but it's very useful. And that's what I use. So to submit your job script, you just type in sbatch. You can hit tab. And I've only got one file there, so I can hit RU and then hit tab, and it will, you don't want to type all those dashes and dots. But your file names, make them useful so I can look at that and I know it's a job script that runs FastQC version 0.11.9 and it's made for Grace. All right, so now I requested 2 service units. You can type in SQUE-me. It will show you your jobs. Right now, this job is running. It's been running for 3 seconds. I scheduled it for 1 hour. It's going to charge me 2 service units, but it's going to complete in it's probably already complete. Up arrow to do my last command. So now it's complete. It's not there anymore. It's complete. If I do ls, you can see your results files. That's output directory. That was one I made earlier. So that's not part of FastQC, but those are the files I created. You can see I've got 2 HTML files, zip files that has the images in it, and then standard out and standard error files. Those are the standard out and standard error files are named in my job script. Okay, so I'll let everyone do that, and we'll take a 10-minute break, and be back here 11:25. And then if anyone has any questions about this exercise, you can ask them now. Anyone have any questions or about this?
Can I see those slide and you have a lot of comments.
Oh, okay.
Comment line on the web.
Yeah.
So can we look at those slides so they can follow and paste those?
Oh, you want to find the slides?
Yeah. So there's a lot of comment line that you screen highlighted.
Oh, can you highlight it from here?
No. What I'm saying is you just going through the slide and then each step you have highlighted some of the comment line. And can you look at those slides?
Yeah, the slides are available where you register for the course.
Right.
So training, courses, next generation sequencing, view the details, and then the slides are available right here. That's what I'm looking at right here. I'm viewing the PDF. Couple people, okay. So the next command is to unzip the zip file. That's where the images are. So back here, DR34, we're gonna do the first one, okay? Now it shows you what it unzipped. And if you're using a terminal, a Mac terminal or Linux, or you can use these links or EOG. Links is used to view the HTML files. EOG is used to view the images. So you can do links and the name of the file, or you can. Oh, okay. Links. You don't need. It's links is actually a non-GUI HTML browser. R1. Okay. So it basically takes an HTML and allows you to view it in text format. So this way you don't have to open a browser. You can take a look here at what passed. Oh, there's a failure here. Then some warnings. That means just review it. Something could be wrong there. So there is one failure. Camera content. This is. It doesn't show what version of FSQC this is. But this is an older version of FSQC. They used to show the camera content by default, but now you have to specify show me the camera content. So that's why it's not showing up here. Okay, so there's a failure here. So we need to queue to quit. Yes, I want to quit. Okay, so we need to view what the failure is. So let's go to files, Scratch, and I create a directory called NGS class. I'm going to just do it here. Yeah, it might be easier. I have a lot of files. So here, HTML should be able to view. It doesn't show it here. I think you do view here. No. It used to show up HTML. Okay, but anyway, we can view the images. So the images are in this directory, images. And we want to look at the per base quality. Okay, there it is, image, per base quality. You can see green is good, yellow, okay, red, not so good. Generally, what you see is Illumina reads have very high quality. When it gets into 300 bases, 250, 300, the quality is a little bit lower, but you can see like 75% of your data here is in the it's actually orange or above. So you can do some trimming here if you want. Some software recommends don't trim. It's part of their software package. They'll do the trimming for you. So read the instructions. GATK is one that says don't trim first. They handle that in the software. All right, here's the output. What does this mean? If you look back at the FASTQ files, this first little plot here shows you the average or the range of all of the first base for all of your sequence reads. Here's what it is. There's a median line, that's the red line, and these are in quartiles. So the upper 25% of your data is here. The middle, the upper 50% is above the red line, and the lower 25% is this line here. So that file that we saw, there's not a whole lot down here, but trimming may help. So basically, after a while, it does some bending, takes like 5 files and bends them into one of these little plots. That's just for reference. So now the one that failed is this one right here. And you can see this is GC content. So A is green, T red. You can generally, A and T are going to be the same amount. G and C are going to be the same amount. But right here, you've got this weird pattern here. So something happened here. Don't know what it is, but it looks like it's some sort of pattern here. See? Looks like an M. And then you've got this towards the end, which could be some adapters at the end. So now you might think, oh, I need to trim the first 20 bases off here. But that's not necessarily the case. In this case, you need to know a little bit about this, how the data was, how this sequence data was generated. This was generated. Go back to the slides. Oh, where is it? Okay, here's the camera profile, which actually is not in the newer version, but you can see also towards in the front here, you've got all these cameras. Kind of corresponds to what we saw in the previous slide. Blue is good. The entire flow cell looks good. You can't really see here. There's a little bit of shading here, but overall it's really good. There's a couple of places here. You can see this track here. It's still good data here, but this will give you an idea if something's wrong with the flow cell. Let's see. Okay, let me get back to this. What this is. This is the way this. Remember I told you about how the DNA is fragmented? There is some mechanical fragmentation, or there's another way to do it, which is using transposons. These transposons will go and recognize a motif on the genome, and it will cleave it right there. So this is the motif it recognizes. And so this is still part of your genome, but it just so happens that it selects the same motif where it cleaves the fragment. So that's why you see this in the front here. So if you see something like that, talk to the sequencing center and ask them about it. Here's an example of what this QC profile looks like, something of a sequence run that failed, or what you can consider failed. It just looks horrible. You don't see a lot in the green and then slopes down to the red. You just see it all over the place. A lot of this is in the red. Hopefully you won't get something like this from the sequence center, but what this was it was an expired kit. These kits, in the past, they expired. I think now they don't have an expiration date. They don't have to be refrigerated or something. But this was a kit that we had in the refrigerator that was given to us for training, but we didn't use it. And then we decided to use it like 9 months after it expired to see what it would look like. And this is what happens. So chances are you won't see that. Here's something else. Someone in our lab ran DNA sequencing. They did their own library prep, and they loaded the machine and ran it. And then when they saw this, they said, well, there's something wrong with your sequencer. Look what happened to my data. Halfway through, the sequencer failed or something. This ain't right. you expect it to look like this first part here all the way across, but then towards the end, it just looks really bad. So what this is this is camera enrichment towards the end. And if I don't have the image here, but if I was to look at the quality scores, it starts out really good and then it just goes down to the red. So it's the opposite of this here. And he was sure, or the person that sequenced was sure that our machine was no good, something wrong with it. But it turned out that it was the library prep. The library prep wasn't 100%, and there were a lot of adapters still left on the fragments, and so that's what's being sequenced here. So they redid their library prep and resequenced, and it looked fine. Here's another one, flow cell. Faulty flow cell. We thought it might have been when we were cleaning it, it got messed up, but no. I think when I said that's a faulty flow cell, and they sent us another one. All right. So any questions on that? Okay. There's a few tools. Trim-O-Matic is really good. I think another one's called Trim Galore. Trim-O-Matic will maintain the read pair order after it does trimming. And if there's, let's talk about this. Looking back at our fragment, if we have these two fragments and we trim, so this represents our single fragment, two ends that are sequenced. If the second read is trimmed to 50 bases and we have a minimum read of 40, these get put into the trim file, pair 1 and pair 2. But if we set up, if this one gets trimmed to 20 bases and our minimum length is 40, it gets thrown into a different file, single end reads, because you lost this pair, you threw it out. This is about overlapping. Fragment 1, there's no overlapping. 2, there's some overlapping. So these two, you will have a left and a right pair for this one. But for this one, you can combine these two because we know DNA is complementary. So we know the rest of this sequence here, this gray part, because we've sequenced the other strand. So we know what this is. So you can merge these two into one longer merge read, and that would go into a singleton file because it's a single read and doesn't have a pair. We've already merged it. This might be useful in some workflows. It might just be an extra step that doesn't provide a lot of utility, but it could be useful. There, we have tools for that. All right, mapping reads, BWA is very popular. Bowtie 2, Bowtie, those are popular. We have a lot of genome indexes. Look in this directory, see if you find a genome index. If you don't, we can add it. It'll save you. That way you don't have to use up your file quota and disk quota to have these genomes in there. So when we index a genome, we index it for STAR, HiSat, SAMTools, Picard, and BWA. So we create an index for a lot of different tools. So it'll help if you that way you don't have to create the index yourself and save it. You can just have us put it in a shared location, and we'll create all those indexes for you at once. All right. Let's go over this. Here's an exercise I worked up just to get you familiar with SAM files. And so what we want to do is go back to our directory in GS class. This one, actually, you can see the underscore there. Okay, we are here. So I'm going to type in this command. I don't think I can copy here, but I'm going to create a symbolic link. Scratch data bio training alignments and DR34 SAM. Okay, so second one is I want to create a link to the genome. Training genomes. So notice how I was hitting tab. Okay. Okay. So to do this exercise, I created a symlink just to save you from having to type in that full path when we run these commands. You don't have to create symlinks whenever you use this viewer, but it's just as an example for this class. So is anyone going to work through this? Okay, so did you create the symlinks?
Yeah, I think I did.
Okay, so if you look, I'm going to clear the screen. If you do ls-l, actually, I think I missed one. Okay, the SAM is here, but I don't have the reference genome. So I need to do the second one again. Oh, I'm sorry, I did ls. I need to do ln. ls, I was wondering what was going on there. All right, so now there's my reference genome. I just need to give this short name, and it's going to point to this other. In order to see where the link points, you need to do ls-l. It'll show you where the link points to. Notice the link is a light blue. If I was just to do ls, you'll see a light blue that indicates it's a pointer to somewhere else. Okay. So you have those two commands. Okay. So now we're going to load. We can view the SAM tool, the SAM file. The SAM file is a text file. It's not compressed. Okay. You can view it with the more command. More, print to the screen. You can look at it. It's just so long. You can use the less command. The less command lets you go up and down. The more command does not. And the less command also will not save it to the screen. So if you want to look through it and save it to the screen so you can copy and paste, use more. If not, you just want to browse it, use less so it doesn't fill up your terminal. You can see the sequence names, the very first line here. Chromosomes 1 through 7 are, and the lengths, and then the technology here, the platform. This is a BAM file or SAM file. The alignment was the alignment was created using BWA. Here's the command. So it gives you a little history of how this was created. Q to quit. All right. So now this file is aligned to the reference genome, but it's not sorted. So when we sort it, we want to sort it on coordinates. So we want the very first line in the SAM file to be chromosome 1, position 1, if there's anything there. Okay, and when you go to chromosome R, it's going to be the last file, the last entry. So first we need to load SAM tools, module load GCC 1020, SAM tools. SAM tools 111. Okay. And then the command is SAM tools sort. Let's see if I can put these here. Okay, the command is dash. This at means how many cores for sorting. So this is going to be quick, so you can do it on the login node. M2G 2 gigabytes dash O. The output's going to be, we're going to call it BAM. So the output is going to be BAM. And the file we're sorting is SAM. Okay. So hit enter. It's going to do sorting. It's already complete. So now you can see we have a BAM file right here. Okay. So in order to view this BAM file in a viewer, you need to create an index. And the index is basically just BAM with .bai. The way you do that, you use SAM tools. The index is going to be for the BAM file. Okay. That's quick too. So once you get the index made, you'll see this bam.bai. Basically, it takes the file name and just appends .bai, BAM index at the end. Has everyone got that that's working on this? Okay. So now we have the BAM file, the alignment file, we have the index, we have the genome all in our directory. So we can go to the next step. All right. You can run these. You can view SAMTools view. You can view the BAM file, but you need to pipe it through more. So it shows you one page at a time. Otherwise, if you do SAMTools view in the BAM file, it's just going to scroll, and you have to hit Control-C. See, it's just going to scroll, and you got to hit Control-C, and it might take a while for Control-C to even register. So if it does happen like this, just hit Control-C and wait a bit. Otherwise, that's why we want to use the more command. If you just want to view the header, you put -H, capital H, for the BAM file, and it'll show you just the header. If you want to view the header plus alignments, if you don't use any option, it's just going to show you the alignments. But if you want to view the header plus alignments, use the -H lowercase and then pipe it through more. Okay. My screen is really short, so you're going to see. Remember, this line wasn't there earlier, but now that the BAM is sorted, we actually see that this is sorted based on coordinate. Some software wants a BAM file or SAM file to be sorted into a BAM file based on the read name. So in that case, you might see SO : name. But most of the time, you're going to want it sorted by coordinate. So that line was added in there. I think even it shows you the command that was used to sort right here. This is the command. It saved the file, the command used to sort. So you can look at kind of a history of what happened. There was the alignment was done using this command. Then the sorting was done using this command. Q to quit. All right, what's in the SAM format? Is it useful to look into this? One thing that's useful is the flag. There's a option in SAMTools called flag stat. It gives you the statistics of the flag. The flag is there are a number of bits here. So notice these bits are numbers that are not duplicated. And to get a flag of 99, there's only one combination of these numbers that you can sum that equals 99, and that's this. So now 1, 2, 3, 32, and 64 define characteristics of this alignment. I'll show you the next slide what those mean, how you can determine what the 1 means, what the 2 means, what 32 means. But for now, let's just say 2 is these 2 means they're mapped in a proper pair, meaning they're on the same chromosome and they're in the correct forward reverse or reverse forward order. So this is a way to keep only reads that are mapped in proper pair. You might want to do this just as a test, or maybe you're doing some special analysis, or you may just want to keep the entire BAM file, but this is a way you can use these flags. So -F is the flag to keep only, lowercase f is to only keep ones that have a 2 in it. So this is a 99, but that 99 was built with a 2, so it's going to keep this entry. If the flag is 1, obviously it's not going to have a 2 in it because 1 is I think 1 is unaligned. Capital F means keep everything except 1024. 1024 is PCR optical duplicates. Let's say you wanted to keep everything except underlined reads, then you would say dash capital F1. I don't want the underlined reads. I want to make my BAM file smaller. Okay, that's what those are. You can run those commands if you want. Then you can copy and paste directly from the slides. There's a tool here. It's very useful if you want to figure out what these bits mean. You just type in the flag 99 and it will check the boxes to let you know. This bits here is something I added. The website doesn't show you this, but 99 is 1. The first one's 1. So it is a paired read. It wasn't underlined. Underlined, I think underlined will be a 0. So this means that the read is paired because it has a 1 in it. It has a 2 in it. It's properly paired. The mate pair is on the reverse strand, and this is the first in the pair. Okay, so that's what 99 means. And if you want to use these flags to keep a group of alignments, you can do that. What we saw on the previous slide. So flag stat, it will take the statistics of the flags and give you a summary. So let's run samtools flag stat in the name of the BAM file. Okay, yeah, I typed it in wrong. Okay, so that was pretty quick. So now you can see it's given us 2 values here, 0 plus 0 mapped right here. This is useful to know if 90 plus is really good. If you see mapped 10%, that means you're probably using the wrong. It could be that what you sampled is not what you expected to be sampled. I've had several sequence samples and I did alignments on all of them, and all of them were 90 plus, except one was like 5%. That was a contaminant from a different organism. So I took some of those reads, I blasted it, and found out it was a different organism than the one that we expected. So we removed it. So this is useful to look at here. What was the percent alignment? This second one just means this first value is a past QC. Right now it's showing they're all past QC because there's not a failed flag in the BAM file. That's why the second one says plus 0. Properly paired, 57%. It could be that also properly paired, it could be that they're farther apart than expected, but for the most part, what you want to check is this 93% alignment. 2% singletons. Okay. All right, let's view. You can actually view the BAM file, samtools tview, and the BAM file. Not the SAM, the BAM. Remember, the BAM has the index. So now since this was sorted, this is chromosome 1, position 1. We don't see a reference. Where these ends are, that's where the reference sequence goes, but we don't know the reference sequence because we didn't provide it. We're only showing you alignments. So look, these 3 here, these bottom 2 here, they have the same start and end alignment coordinates. You can see over here, they stop here. So this is probably a PCR duplicate. Like when you increase the DNA that's in a sample, you run PCR and you get more fragments, more of the same fragments. Sometimes you need that to actually fill the sequencer, but when you're calling variants, you'll want to remove those duplicates. So that's why you see these start at the same place and end at the same place. It's just showing you the colors, the underscore, the capitals or lowercase. Those are all indications of the quality, either if it's on the reverse forward strand or if it's low quality alignment, or if it agrees or disagrees with the reference. But we don't have the reference here. Hit Q to quit. The next one we're going to add in the reference. So just type in tview or just up arrow, save you some typing, and then type in C_tab. So we're looking at the BAM file. We're also providing samtools the reference sequence Now the reference sequence is on top, and we don't see all these alignments. This is probably has something to do with the web browser, but there should be like underscore all the way across so you can see this like I have it here. So yeah, this is it's probably better to use the terminal because we're not seeing the underscores in this web browser. But I do have an image here, so this is what you can expect it to look like. And you've got the reference at the top. Wow, that you can't really see that here either. Maybe you can see it better on that screen, but there's some blue underscores here with dots or commas. That's you can look at the help and see what the dots and commas mean. Okay, so Q to quit. The next one is actually, if you start this and hit question mark, it'll give you a help menu. Okay, and it tells you some things. Some of this is not on the help menu, so go to the website and see what this other stuff is about, the commas and. Okay, now if you want to go to a specific coordinate, you can't just scroll through it. You'd be there all weeks and months trying to get to the end. But if you did an analysis and you know where there is a SNP, then you can go to that coordinate by just adding the coordinates. In this case, I know there's a SNP here, chromosome 1, position 315398. So up arrow dash P 315398. I say 315398. All right, now you can see how this SAMTools TV shows you where the SNP is. And I'm going to hit the left arrow just to bring it over here. Oh, this is not good. Go too far, it missed. This browser's, looking at this through the browser's not good. See, notice how it shifts over. It shouldn't do that. Okay, so you'll have better luck with this on the command line. But you can see how the dots and commas mean that it's the same base as the reference, but if it's different, it'll show you what it is. So here the reference is a C, reference is C, and your SNP is an A. Okay. There's a better view of that. I think it's the first time I tried it on. Maybe it might be this browser. Is anyone trying it on the browser? Does it look bad? Like, did it work okay?
It's doing the same thing.
Oh, it shifts over. So I'll have to put a note on here. This is better to run on the terminal. In the past, I had been using the terminal, but the portal is really useful, so I was going to run it on the portal. But I'll put a message in there. I'll update the slides to use the terminal for that part. All right. We got about 30 minutes. I want to kind of go through this next few slides. We have one more exercise at the end. Variant calling, finding SNPs and indels in a sample. We have a lot of tools there. PCR duplicates, I talked about that. Picard will mark the duplicates. It'll still be in the BAM file, but there will be a mark on there. And then when you run your analysis to call variants, it's not going to count the duplicates because that would not be fair. That would be inaccurate, right? Because you created those extra fragments. You want to make sure their individual sequence reads when you're counting variants. So mark duplicates before you start calling variants. There's a few different popular tools here for variant calling. GATK. There's another workflow, SAMTools, BCF tools. There's a Freebase, which is it's a simpler approach than GATK, and VARSCAN. VARSCAN is more flexible, but I think it can be too flexible, and you need to be careful with the options you use. But GATK, I think we also have that in an image called Parabricks. I think that does variant calling, and it's really quick because it runs on GPU. But if you're looking for, if you just have a bacterial genome or fungal genome, Freebase is really good. It's simple to use, and it's a well-maintained tool. All right, VCF format. you can look through this and Google and look online, but I just gave you a reference here. There's a lot of information. Get familiar with this if you're doing a variant calling project. There's a lot of information. The map's at the top, which corresponds to each of these lines. It'll show you the depth of alignment. The DP is the depth. So at this chromosome 2 position, there's actually a known SNP or a known variant. It's in dbSNP. This is the ID for in dbSNP. It's known. You can go in there and see what other people have done research on this before. The depth is 13. There's 13 reads that are lined up, not counting the PCR duplicates. If you're going to call this, if you only have a depth of 1, that's not a variant. That can be a sequencing error, right? So you have to have a minimum value of minimum depth to actually call it a variant. Usually it's about 10, a depth of 10. You can change that to be more lenient of 5 or make it more stringent, change it to 20. But usually the software has a default value. But definitely a depth of 1 is not good to make calls on. Here's a paper. It's actually getting a little old now, but it did this. If you run this again, you might get some different numbers. But when this was run, compared Freebase, SAM tools, and GATK, and saw that about 90% of these were all the variants called in all the software were found by all 3. Some found some that were or marked some as variants that weren't called by others. So it might be helpful to use more than one tool, or to be aware that some of this, maybe this 2% in Freebase is, it could be useful or it may not be, but you'll need to find some way of doing a secondary analysis to verify that. Okay, here's a useful tool that will do a conservative sequence analysis. Basically, it uses SciBlast and it looks back at other genomes, other organisms that have that same sequence, protein sequence, and it does an alignment and it says, where I have this SNP, 100% of all organisms are conserved. This is very, very highly conserved. So there's not a lot of, there's not any variants here. And maybe not be 100%. It could be, but it could be high, 98%. So which means that if you have a SNP in that region, it could very well be important, because if it's found in almost all organisms, but you have a variant in your disease sample, then that's a flag saying, hey, this is unique to this sample. It should be highly conserved, but I have a variant here. If you go into a region that has very low conservation across all the sequences, chances are it's not vital to the health of the organism, and it can have this variation and it can still be vital. So that will have a different score. So this will tell you it'll tell you the consequence of the amino acid change. So if the amino acid is detrimental, which means it's in a highly conserved region, it will let you know. Otherwise, it will give a different score and say, it's common to have a variation, a sequence variant in this region might not be so critical, but this could help. Annotate variants. SNPF is really good, well maintained. Developers are very responsive if you have questions. They have a lot of information. A lot of databases are already pre-configured. So I recommend this if you want to annotate. You can see they have over 2,500 pre-built databases, probably more since I made this slide. All right, JBrowse. This is viewing JBrowse. This is viewing an alignment. These are the alignments, the BAM file. This is a different track showing you the VCF file. The VCF file will show you where in JBrowse will highlight this SNP. It will show you what the variant is from T to a G. And if you look here, it's only going to show you what's different from the reference. So this is heterozygous SNP. This is a diploid organism. So one of the homologous chromosomes has a G in it. The other one has the reference, a T. So that's why you see about half of these have a G in it, and the other half agree with the reference genome. This is homozygous SNP. Both of the homologous chromosomes have this variation in it. Okay, so if you're doing a haploid, mostly you're going to see this most in almost all of your variants. It's going to be because you only have one chromosome, right? Unless you have a mixture of the organism your target organism between a closely related, but it doesn't have the variation. But generally for diploid, you're going to see something like this. I just threw this in there. There's a sequencer. I don't know if it's used anymore, but if you hear the term sequence strand bias, that means that all the positive strands can have a variation and all the negative strands have a variation. That's due to the sequencing technology. Ion Torrent, they're newer sequencers. I'm not sure, but it may be different now. But anyway, they do have software that recognizes this strand bias and it will pass this and say, this is not really a variation in your genome. This is strand bias created by this machine. But I just wanted to let you know in case you hear that term strand bias. RNA-seq. Lots of tools here. We have a lot of information. We have a lot of users that do RNA-seq. There's some packages in R and some software like Trinity. This is just saying which is better, to take more samples in the field or to take your sample and sequence it more times. Which do you think is better? It's actually better to take more samples in this field, more biological samples, than to take a single sample and sequence it 5 times. All right, looking for tools, just do Module Spider. These are some of the popular tools. Trinity, you can actually spider 2 tools at the same time. Module Spider HiSat 2 and cufflinks. String tie is often used. Trinity. It's called Trinity because it has 3 different steps. You can read all about it. So when you run Trinity, Trinity runs it creates a lot of small files as it builds these assemblies for the transcripts. It can create 200,000, 300,000, 500,000 files, depending on the size of your genome. You can work this into the temp directory. An approach is to move everything to the temp directory, do the analysis there, copy the results back. We do have a job script for that, and we have documentation on our website that shows you how to do this. Use the temp dir if you can, but realize that if you put everything in the temp dir and your job fails, all the data's lost. Not your input data, but the analysis results are lost. So if your job is not complete, if it fails halfway and you're in the temp directory, there's these checkpoint files that get saved. Those are deleted also, so you have to start from the beginning. If it's a small genome, it might be good just to use the temp directory. If you have a large genome and you think it's going to fail or it might fail, you don't want it to run for 4 days in the temp directory and then fail and have to start over. So you may want to just run it in the scratch. But in that case, you will need to request an increase in your file quota so that you can accommodate hundreds of thousands of files. All right, ChIP-seq. Just quickly, basically ChIP-seq is you're taking you're checking where a protein binds to DNA. So you have this antibody that recognizes that protein. It binds to the protein as it's bound to the DNA. That's this here, so that we have this example of a protein binding to the DNA. Fragment all this. I'm missing an image here. That might just be, I don't know what that is. So now you need to wash away everything that doesn't have the protein on it. So the way to do that is you bind it with an antibody that recognizes the protein. Wash everything else away, all these that it didn't bind. Remove the protein from the DNA and then sequence it. So now you've got this region of your genome across the genome that the protein bound to. You can do sequencing here, and then when you align it, you're going to see you're going to see these peaks. So you hear a lot of peak calling when you're talking about ChIP-seq. That's what this is. This is a peak here. This is alignment depth. So so these alignments of whatever you oscillated here are falling in this region here. And then you do that across your whole genome. The peak, the DNA is not going to be the exact same. It's going to have like a motif. So you can create this motif image like this based on all these peaks across your genome. And the Seq logo is here to create that in R. If you want to create that logo. And then we have the tools like Max, Deep Tools, Sicer. Those are used a lot by our users. Again, if you see a tool that's not there you need to use, let us know. We can install it. Most of the time we can install it. Very rarely it's not able to be installed. Sometimes it's because it's a Windows only tool. It's rare that's a Windows only tool, but sometimes it's just it doesn't work on the cluster, but that's rare. If you have a lot of commands to run, and like in the left in this box, we have this tool called TMU Launcher. It will take those commands and run them across one or more nodes. So you can run, instead of running one command, then running the next and waiting for each to complete sequentially, you can run them in parallel using that tool. You can look on the website. I'll need to add a link to the website for that. But I'll add a link to that to see so you can see how to use that. All right, this is the last section. This is an exercise to learn how to use containers. That we're going to be able to get through this. So what's a biocontainer or a container or an image? So basically, some software is very complex to install. It has all these dependencies. You have to have specific versions, and you have to have these databases configured, and to install it can be a pain, and sometimes almost impossible to replicate the way they installed it. And it's just too much time. But hopefully they provide a container or an image, Singularity image, a Docker image, so that basically it's all packaged into one image, and you can use that image to run the software. It's already installed in this image. Good thing about this is it's already installed. There's all the dependencies are there, and basically you're replicating their software installation. One of the cons is sometimes the image isn't available for the latest version of a software. You have to wait until someone generates the image if you don't do it yourself. But some software is basically may only be available as an image. This is different than the modules. When we do modules, loads SAM tools, that loads it in SAM tools in the command line. But an image, you have to go into the image with the command line. I'll show you how to do that. And then run it from within this image it's already built. Okay, we don't have Docker on the clusters, but we do have Singularity. Singularity, you can use that to take a Docker image and change it or translate it to a Singularity image. And then you can run the Singularity image on the compute nodes. So you can't run Singularity on the login nodes, but you can on the compute nodes. And we're going to do that in a minute. So compute nodes don't have internet access, but we do have a web proxy that you need to load to have internet access. Okay, you can also run once you have your Singularity image built, you can use that in your job script. We do have a lot of images already available. You can find images on Docker Hub. Here's a biocontainers directory in Docker Hub. Search that. There's another one called QAY.io. Some of the popular containers that people use, AlphaFold. There's some other. You can find SAM tools in here too, but since we already have it as a module, you don't need to download SAM tools and get through that. So we're going to build a container. So basically what we're going to do is, since this needs to be done on the compute node, Singularity is not on the login node. So in order to get on the compute node, you can either start a VPN session, a VNC job. Let me close it. And the way you do that is Go to our main website. Portal. All right. So we need to get to the compute node. If you click this interactive apps, you can launch a VNC session. VNC session will it launches a job script basically and lets you go to a compute node. Then you have a terminal on the compute node that you can do this on. But we're going to do a little shortcut here. We're going to use the srun command. The srun command will do this on the command line. So let's come back here. I'm going to run this srun command. Control L to clear. You need to give it a time. I'm just going to do 1 hour. 1, you can do 1. 0 minutes, 0 seconds. Mem equals. We don't need a whole lot, so we don't have to use the whole compute node. We only need one task. Okay, so basically we're going to launch a job. Notice the prompt, it says Grace 1. I'm still on the login node, Grace 1. Close that. All right, I'm still on login node, Grace 1. But when I do srun, it's going to take me to a compute node. I'm actually launching a job with this command. All right, waiting for resources. It's been allocated. Now look, I'm on compute node C781. So I'm actually on the compute node now. So when you do this, if you request 2 CPUs, don't run 48 CPUs, okay? Because there's other jobs running on this node and you only requested 2. So if you're testing software this way and you can specify a number of threads, make sure it matches whatever you set this to. Because it'll basically just slow down your job and everyone else's job on there. So the next thing we want to do is we're on the compute node. There's no connection to the internet. Load the web proxy module. I actually have something there. Module purge. Module. There's not really a version here. It's a module to connect to our web proxy. So just do module web proxy, module load web proxy. You may need to do module purge also. All right, now we have a couple of commands here. These commands are basically to use the temp dir. Remember we talked about temp dir. This is going to help you when you do these singularity builds because it's going to save everything to the temp dir. It's going to be quicker and you're not going to hit your quota. So let's type in the next commands. Okay, but let me show you something right now. Now we're on the compute node in a job, and now the temp dir has a value to it. Okay. All right. Make sure I typed that in correctly. S registry and singularity. Okay. So now whenever I'm downloading this image from Docker Hub and changing it into a singularity image, it's going to save it in temp dir instead of my scratch. So singularity, I hit tab. Okay. You can do latest. I think you can do latest. If there is a latest link, or you can just do this, but you're not going to know what version it is. So If you go to the Docker website, it'll show you what version is available. So that's why I know what version's there. This is the command. The command you'll see on Docker is a little bit different. But basically, this is the format: Docker : file containers, and then the tool and the version. So hit enter. That's going to take a few minutes. Hopefully you see this. All right, while that's working, let's see. Building, should we use all the entire node or just a few cores? It's just showing you that if you do use a few cores, it takes about maybe 4 minutes, 3.5. If you were to use the entire compute node, maybe 2 minutes. This is Blast. That's a single tool. But if you have a really complex installation with several tools, that might be a larger image. But generally, you need to use the entire compute node. You can put, let's see, you can put this into a job script. That's what this page is, job script, and submit it as a job script. That way you don't have to go interactively and wait for it. Okay. See, it's still going. That way, if I need to go to class, I can just submit the job script and come back and it'll be done. The job script runs while you're away, right? You can disconnect from your session. All right, so it's creating the file. Is anyone running this? Still creating?
It just finished.
Okay. All right, well, that's still going. Now that you're on the compute node, you can use the Singularity command to run BLASTP that's in your Singularity image. And the command is Singularity exec, the name of your image, whatever tool you're using. Okay. Still going. So you can do BLASTP-H to show the help for BLASTP. You could actually do ls-l. You can do $PWD, or not $PWD. Well, you can't do that, but you can do PWD to see what directory you're in. Basically, you're searching another. It's almost like another Linux file system. What's in that file system? What tools are there? Where are they located? Okay, mine's still going. Or if you want to just run it and get a prompt, you can type in Singularity run and then the name of the Singularity image. Basically, you get to a prompt, and basically it's like you're logged into another computer. You still have the same resources based on whatever your job is, but now you're on a different system that has BLAST and maybe other tools. Okay, so just enter that in. Has anyone entered BLAST-P-H? And you see the help for BLAST? P? Yeah.
It's like blast.
Yeah. So you can also do, I think blast in-h. So it probably has all the blast in, blast in, all those blasts in there. Okay. Now let's do this first command. I'm going to clear the screen, Control L, Singularity, blast image, blast 8. So I'm basically going into the image where blast is installed. And it's giving me the help, okay? If I wanted to see a different tool, I think blast in is there also for nucleotide. If I wanted to know in the image where blast in is installed, it's going to show me that inside this image, blast is installed in this directory, opt-conda bin blast, okay? Run, Singularity run. Let's get a prompt. Oh, no. Singularity run and the image name, okay? Now look, I have a prompt called Singularity. See that at the bottom? So now I'm actually inside the image here. Which blast, which blast in? Which blast in? Okay. If I want to exit that, you can type in exit or Control D. Which blast in? It says there's no blast in because now I'm back on the compute node. So back inside Singularity. So now you can go into the Singularity image. You can test it out, blast in, and work on your job script, and then later build your job script and submit it that way. And then when you're done, Control D to exit. Notice I'm still on the compute node. So when you're done working on the compute node, you have a job running now. If I did -me, it shows I have a job running on compute node 781, and that's where my prompt is, 781. So if I want to exit this job, I'm done. Well, let me just stay there until the next slide. I think this is the last slide. This is just an example. If the job script at the bottom here, if the job script is in a different directory other than your working directory, say it's a shared job script, just give the full path to the job script, and then you can run your commands. Okay. Once you work out your commands, you can save these. If you have your own image in the same directory as your job script, you can use that path because it's saying it's in the same directory. But if it's not, give the path to the directory and the image when you're using this in a job script. Okay. All right, these are some useful commands. If I do ls, I've got a number of files here. Let's just say I just ran fastqc, and I'm not seeing. I just ran a job, and I don't know where the output of those files are. So I created. You can call it whatever you want, but you can create an alias, and you can look online and see how to do this. I created an alias called LHL. So basically, LHL, what it does is it puts the newest file on top. If I just ran some analysis, instead of trying to sift through 50 files and say, where's that file that I just created? If you sort it, put the newest on top, it'll save you some time. It'll show you that this is remember, this is the very first thing I did was I saved this template script. So this is on the bottom. And as I went through the analysis, the last thing I created was this image file. That's very useful. I just want to share that with you. You can actually do, if you have like 100 files, if you do LHL, it's going to scroll like this. So you can do the top 10, top 20, and, top 30. You can name it whatever you want. I just got used to calling it LHL. Also, instead of doing SQUE-me, you can create an alias called P and Q for Q, SQUE, and P for PStat. So I basically have Q. Instead of having to type in SQUE-me, I just save myself some time and just hit Q. P is another one. PEStat is showing you PEStat for your jobs. When you say -u and the user, this $user is basically your environment variable for your username. If you just do PEStat without the -u, it's going to show you all the jobs. But I just want to see mine. Now here, I have this job here. I'm on this compute node. Remember, I only reserved, I think, 2. How many cores did I reserve? Just 2 CPUs, okay? So now there's a lot of other CPUs you can see a lot of other jobs are running on this node. So that's why you want to be conscious about how many CPUs you're using when you're logged into this interactively. And if I just did PEStat without specifying user, it's going to show you all the running jobs and all the queued jobs. And so you may just want to see your jobs. All right, that's it. We have a lot of resources online. Like I said, that our documentation is built off several years of experience from our end and from our users. Check our documentation out. Search for it. Search for whatever you need to look for when you go to our documentation. There's a search feature up here. Trinity. Okay, that way you don't have to browse through the menus like that. Okay, use that search feature. Also, it's good if you have an error message. Search for the error message. Let's just say memory, insufficient memory. See, there's unusable memory. If you have an issue with it says your job script ran out of memory, you might find some information here just by searching the error message. And also use Google to search your error messages. So if you have any questions or you need our help, send us the job ID. If you send us your job ID, we can get almost all the information we need. But please, it'll save us time if you say, I have a problem, my job didn't run, what's wrong with it? And you don't send us any other information, we're going to come right back and just say, what's the job ID? So if you say, give us some more information, what cluster you're using, even if you just send us a job ID, we don't know which cluster you're using. We have like 4 or 5 clusters. So send us what cluster you're using. It'll save us some time and save bouncing back in emails, trying to figure out what cluster you're using and what is the job ID. Send us a job ID, send us the cluster. Tell us what you did, what modules you loaded. Probably if you're doing interactively, let us know. If you have a job script, we can look at your job script based on your job ID, what commands are used. That's just a system admin privilege. Not other people can't see your job scripts. What messages you're seeing? If you say my job's failed, I don't know what's wrong. What message are you seeing letting you know that it's failed so we can look for the same message? Maybe you're looking at something different. It's not a failure. Maybe it's just a warning. And then when you submit a request or a help desk asking us to help you out, when it's been resolved and you've got it worked out, let us know so we can close it. The ticket is basically a ticket that we have open, and we work through these. And as they're completed, we resolve it. And then if you have a new issue, just start a new ticket. Or if somehow that same issue pops back up or there's something continuing on that same ticket, you can respond to the ticket and reopen it. All right, that's it. Does anyone have any questions? Want me to go back over one of these slides? No. What kind of analysis, huh? Yeah.
So when we are send some questions to the
Uh-huh.
email, do you want to respond to this, or?
Everybody in the HPRC staff will see the email. And if it's something like Galaxy, for example, if you're using Galaxy and you ask a Galaxy question, chances are I'll be the one that picks that ticket up. Or if you ask a question about Trinity or a job failure, I'll be the one. If you have a question about your accounts, someone else will pick that up. If you have a question about extending job runtime, somebody else will pick it up. So we each have our kind of our specialty of answering help desk tickets. And if you don't get a response within a day or two, just you can respond to the ticket again. But generally, what happens if you say I would like this software installed? Let's just say I see that I'm going to install it. I'll take the ticket, and you should get an email saying the staff has taken your ticket and they're working on it. Just give us some time to work on it. We might be out for a day, or it might take a few days to get the software installed. Or we might be doing other things like teaching. We don't have time to work on tickets. So give us if your ticket hasn't been taken, you don't see that email response, then if you haven't heard anything within a couple of days, then give us a reminder. Maybe someone is not taking the ticket because we're all busy, or because we're unsure of who should take it, or sometimes we'll take a ticket when we know we can handle it. But if we're unsure, we might be asking around in our group and saying, who can take this ticket? Because some software we're not familiar with, we might tell you, go check Google users groups, go check user groups in the software. Maybe they'll have more information, more experience with it than us. We can help you with job submission, job failures, anything related to the Slurm scheduler. But if you say, I want to calculate and then all these long terms and using the software with all these options, we may have never done that before. And we might say, we might know of a Google group or a user group that we can refer you to, but also check. If it's something related to our cluster, we can definitely help you with it. But if it's more specific to an option within some software, you can ask us, but we might just say, check for Google user groups. A lot of times you can just copy and paste the error in Google and you can find a solution. That's basically what we'll do. But you may not actually know exactly how to resolve it, even though you see it, the answer there, but we may know how to do it. But if you do a Google search and you say, I found this, but I'm not sure how to do this, then we can help you. All right, I'll hang around here for a little bit if you have any more questions, but thanks for attending. If you want me to go back over any of these slides, I can. This is being recorded. It was recorded, so we have a recording from 2021, but there are some new things in here that I wanted to include. So that recording, today's recording, will be available in a few weeks after it's processed, removing time, our break time, and the time leading up to when we started. So once that's processed and on the web, you can check it, look for it on the web. Just check the time it was uploaded. Or actually, you'll see the very first slide. It tells you fall 2023. Right now, I think it's 2021 was the recording, but that'll be on the first slide. So. All right, thanks.